back. Now we're going to look at an example describing and demonstrating the bifurcation analysis. This is from section 2.7, phase line bifurcation analysis. Let's first go over the steps for graphing a bifurcation diagram. Well, first, you determine any critical bifurcation points from the equilibrium points you've already found. So if you haven't done the equilibrium phase line analysis yet, do that. Find the equilibrium points, test a sign chart, that kind of thing. So having the equilibrium points, then you determine which parameter values will change the number of equilibrium points or the type, behavior of those equilibrium points. Then two, we graph a phase line for each critical bifurcation point, and then let me put another phase line on either side of each of those. So if we have just one critical bifurcation point, we end up with three different phase lines, one fixed and two that are varying around it. If we have two bifurcation points, we have 1, 2, 3 around those, so 5 total. And what these bifurcation diagrams do is they represent the slope fields kind of like in a bookshelf. You can think of a shelf of books where each book, when you pull it out, is a slope field. When you put it back, all you're seeing is the phase line, and you're seeing a progression on those phase lines. So let's, at the very end, you finally show that progression by connecting the dots. So let's do a quick check example here. This is x prime equals ax times x minus b squared times c minus x, with a, b, and c all being positive, but we don't know exactly their order. So the equilibrium points, based on the factored form, are 0, b, and c. Okay, so are there any parameter values which change the number or type of equilibrium point? Well, we know that b and c are different than 0, so that is always distinct. But b and c could equal each other. And when they do, you only have 2 equilibrium points. So that right there is the critical bifurcation point. It's when the parameter b equals the parameter c. So I graph that one phase line, and then I graph a phase line on either side, b less than c, b greater than c. And each of these phase lines are representing the x axis. Then on those phase lines, we graph circles for the nodes, the equilibrium points, and we determine whether they're stable, unstable, or semi-stable using a sign chart. So for the first one, when b is less than c, you have 3 equilibrium points with b in the middle. When b equals c, you only have 2. You can see that critical bifurcation happening. And then when b is greater than c, you have 3 again, where b is jumped up. So let's do a quick sign chart for these. Starting on the left, at the bottom, negative, you can use negative infinity. You have a negative times a positive, because it's squared, times a positive. So that is a negative going down. And then at positive infinity, you have a positive times a positive, it's squared, times a negative. So it's going down as well. Now I do these two, the extreme points, first because they're the same across all the phase lines. Doesn't matter the values for b and c, we always have the same pattern at the extremes. Now let's look in the middle. When b is less than c, we want to look at some value of x between 0 and b, still less than c. So here is positive, x is positive. X, it doesn't matter here, this is going to be positive. And then c minus a value less than it is going to be positive. So we have all things positive going up. If we shift it up a little bit, we're still less than c. This middle term is positive. b really doesn't change anything. This x is positive. C minus that value less than it, still positive. So we end up with a sink, a semi-stable node there, and a source. moving on to the middle, we have B and C equal. Again, this middle term is positive. If we have something in the middle, x is going to be positive, so that's positive times positive. It's less than C, positive, which makes this a source again, and this a sink. And then finally, when B is greater than C, we look at the value when x is positive and less than both B and C. Positive, 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 going up, which makes this a source. And then between C and B, positive for x. This is positive because it's squared, and this C minus x is negative. I'm bringing it down. So C, and then B is semi-stable, filled in from the top. So let's look at the dynamics. We shift from 3 equilibrium points, 1 stable, 1 semi, 1 unstable, to 2, 1 stable, 1 unstable, to 3 again, similar here, but the order is swapped. So now let's track the trend, the movement. We can see that there's a consistency in the 0 value being an unstable. So then you go up a little bit and you say, what about C? Well, C is also consistent. It is stable the whole way. Okay, so we connect those pieces together. Now, what's the other trend? Well, B starts out as semi-stable, then B merges with C, and then comes back out. So what we do is we draw dotted lines for unstable and semi-unstable. It merges and then keeps going. So that is your bifurcation diagram. Shows that you have an always an unstable node at the bottom. We have always stable node or stable sink on top. And then this semi-stable node that kind of slides through a little bit. And if we were to graph these, let's make some space and graph the 3 slope fields. For B less than C, we have zero. Like that. The solutions will diverge from the unstable, the source here. They will diverge up as well, level off like a cubic function in this case, and then level off asymptotically there. And from above, converging asymptotically. So there is a family of solutions for the first case, pulling the book out from this spine, the phase plane, turning it into the slope field. When B equals C, what happens? Well, this just slides right up. And your solutions from above are the same. Solutions from below on the very bottom are the same. In between, are smoothed out a little bit. And then for the last case, B greater than C. I still have C there, but now B is above it. And from our quick diagram here, it's filling in from above. So our solutions will come in, just level off just briefly. Oops. And there you have it. Here is the bifurcation description. Based upon the bifurcation diagram you can see here, when I connected them, I can see this movement of the equilibrium point B, which is semi-stable, and as it shifts up, we get to a point where it kind of simplifies the graph a little bit. This is very similar to the logistic growth model, a little bit different. And then we get up to a point where it slightly changes it again. Kind of levels off, but then comes back down again, kind of acting like a cubic pattern. So there is an introduction to working with bifurcation diagrams. Remember that they start off with phase lines, which means you need to know your equilibrium points. Then from the equilibrium points, you check to see if there's any parameter value that would change them, either in terms of changing the sign out here or of the slope. In this case, A didn't impact it because it was always positive. Or changing the number, in this case, B equals C. And then once you have those representative phase lines drawn out, then you can connect the dots together to see the movement of the shift between one slope field pattern in terms of the solution leveling off below C to another pattern where it's leveling off as it comes down back to C. Okay, that's all for bifurcation.